This is my 24 bay 4-node GlusterFS storage cluster made with mostly 3D printed parts, 4 Raspberry Pi 5s, some old Dell storage sleds, and a bit of jank. Now I wouldn't say it's the fastest solution out there, and it does require a bit more than a few clicks to set up, but I'll tell you what, it's power efficient and it's cool as hell. Alright, outside of just wanting to build something cool, why would I do this? It's not like a 24 bay storage server is that difficult to find or expensive to come by. Well, I'm not gonna lie, building something cool was kind of the main driver here, but I also just like clusters. Over the years, I've built tiny Proxmox clusters, some bare metal K3S clusters, a 45 drives cluster, a Docker Swarm cluster, and I just think the concept of high availability is fun to mess around with. This system is different than all of those in that its primary purpose is storage, and I'm using a software that I've never used before, GlusterFS. So where do we start here? I guess I should mention that the inspiration for this project was a tweet from the Zima OS people about a guy who built a storage server with a bunch of drives connected to a Zima board too. And since I already had this 12U 10-inch mini rack sitting around from a previous project, I figured, hey, I like wasting money. I like home labbing. Maybe I could build something like that. I figured to change it up, I could also reuse my 4 Raspberry Pi 5s from another project and go the cluster route. I'd heard people mention GlusterFS a few times on my videos, so I figured this would be the perfect opportunity to try it out. And at this point, I had my build in mind. I'd have 4 Raspberry Pis, each with 6 drives connected to them using the Pi's lone PCIe lane to run an M.2 to SATA adapter, and with each set of 6 drives only taking up 2U worth of space, this was totally feasible. To power the Pis, I wanted to use PoE like in my previous setup, which used these PoE adapters rather than shilling out money for 4 PoE hats. And since I purchased this GeekPi bundle that came with the 2U mount as well as the NVMe hat for each of the Pis, I figured it would be a waste to turn around and buy another hat just for PoE. This is mainly because they actually have hats that do both NVMe expansion and PoE, but I didn't feel like returning everything. I eventually gave in and ordered these Waveshare PoE hats because I figured if I'm gonna put in all this trouble, I may as well do it right. As for how they're powered, I'm using this Unify Ultra switch, and it's pretty cool. It's got 8 ports and can be powered via PoE or a dedicated power supply depending on how much juice you want to use. I got the 210 watt power supply, which is plenty considering each of these Pis only uses like 25 watts max. Now remember how I said I was using an M.2 to SATA adapter? Well, I'm also using an M.2 expansion cable because with how this NVMe board attaches to the Pi, it would be impossible without it. And now for the storage. I'm reusing the same design from the build that inspired me, which is actually pretty intuitive. It allows you to use these super common Dell hard drive sleds combined with these SATA male to female adapters to give you hot swappability. I will say some of the drives are kind of a tight fit, so maybe more like lukewarm swappability, but it works. Oh, and make sure you have 10mm M3 screws to fasten those down, and the bottom 4 are kind of a pain to do, just letting you know. Anyway, that gives us the ability to connect all of our drives with the regular old SATA cables, but that's a good amount of drives. How do we power all of them? Well, to get 24 SATA power connectors, you're gonna need some adapters. I'm using a combination of 3 things here. SATA power 6-port expanders, a PCIe powered a 4 SATA power adapter, and a CPU powered a 4 SATA power adapter. It's a little jank, yes, but I did actually try to do something a bit fancier. I paid a guy on Fiverr to design me a board that takes PCIe power and converts that to 3 SATA power ports. And I was talking with PCBWay to get this done, but their payment methods are now like super sketchy and it wouldn't have come in time anyway. But I still may order them just to see how they work. Anyway, this gives us plenty enough power from our little 500 watt power supply here, which is the same one that I've used on a lot of my other projects. FYI, every single part I used is listed down in the description below. The last piece of the puzzle is cooling because we have to have cooling. I knew I wanted to use 90mm fans since 2 of them fit so nicely in the 2U space, so I ended up getting 8 of these Arctic fans, which are powered from this little 8-port fan hub, which lets you set them to off, low, or high. Works great. I wanted the fans to be on the inside, but after running the wires, there was definitely not enough room, so I had to flip them around. As for the 3D design here, there really isn't much, to be honest. We talked about the drive caddies, but we also have these pretty generic fan mounts, a 1U shelf to hold the switch power supply and whatever else you want, and a little mount for the other power supply. Funny enough, most of these pieces were actually a few millimeters too big for my Prusa MK4S, so I had my buddy print them out on his Bamboo P2S, which then made me go out and order a Bamboo H2S. Yay, more money. And that's the gist of the build. Before we get into the software side of things, let's talk a bit about the actual storage. Each of the Pis is going to have 3 4TB 5400 RPM drives, one 6TB drive, and two 512GB SSDs. This was a combination of me wanting to have different storage volumes to test and the fact that these drives are what I already had laying around. Would it have been way cooler to use 24 20TB drives? Yeah, but I mean, just for testing, that's obviously a little unnecessary and would only be useful to make some cringe thumbnail about how much storage you have, which is something I would never do. Oh, and the Pis are running 64-bit Raspberry Pi OS Lite from an SD card, because yeah. All right, I think that covers everything. The drives and fans come on using this cool little switch with a 24-pin jumper, and we are off to the races. Except not initially. When I first booted everything up, none of the drives were detected, even though the Pi was seeing the SATA card. After some Googling, it turns out that I had to adjust some PCIe parameters in the boot config, then just like that, we were set up with our Gluster cluster. I will say that with everything running at idle, it pulls around 100 watts, which for what you get here is actually pretty dang good. So the first thing you have to do is get GlusterFS server installed on all of your nodes. We'll be using apt since we are on Raspberry Pi OS. Then use the gluster probe command to ensure that all of your nodes can see each other. If you're good there, then enable gluster with systemctl. You can then check the status of your peers just to ensure you're all set. Next, we need to make sure that all of the drives are wiped and that there are no partitions on them. We'll then use mkfs to slap an ext4 file system on there, which will let us mount each drive. The next step is key in that we're going to create a mount point for each drive on each node, and we're going to keep the naming scheme consistent so that when we create our GlusterFS volumes, it's way easier to understand. You can choose whatever naming scheme you want, but mine just ensures that I know which drive is mounted where. Now, to make sure all the drives are properly mounted at startup, we're going to add the mounts to our fstab, but we're going to use the UUIDs of the drives rather than the device directory since this can change. Get the IDs using the blk ID command and then make sure you keep track of which drive those are so that you can mount them to the appropriate mount directory. Then update your fstab with those 6 entries and run a mount all. And boom. We have all of our drives mounted to all of our nodes, and we are finally ready to create our GlusterFS volumes. So GlusterFS has a few different volume types: distributed, dispersed, and replicated. High-level explanation is that distributed is like JBOD. You get max capacity, but no real redundancy or performance gain. Dispersed is like RAID 5 or RAID 6, where you get redundancy across multiple drives. And replicated is like RAID 1, where all of the drives are mirrored. I'll note here that in GlusterFS, we don't really use the term drives, we use blocks, but for all intents and purposes, a drive is a block. And you're probably thinking, where is RAID 0? Well, in older versions of GlusterFS, they have striped, which is basically RAID 0, but this is being deprecated since GlusterFS isn't really designed for this type of layout. All right, so we are going to create 3 different volumes: a distributed replicated one across our 12 4TB drives with a replica of 3, meaning that everything written to this volume is replicated 2 additional times across the 12 drives. This effectively gives us a RAID 10 setup with 16 terabytes of usable space, which isn't a lot, but this would be for your really important shit. Next, we are doing a dispersed volume on our 4 6TB drives with a redundancy of 1. This is effectively just RAID 5, so 4 drives with 1 as parity, giving us 75% efficiency or 18 terabytes of space. The last is going to be another distributed replicated volume across our 6 SSDs, this time with a replica of 2. I wanted to do this just to see the performance difference between 2 RAID 10 volumes, one with hard drives and one with SSDs. Now, one thing to note is that when you do these distributed replicated setups is that the order that you list your blocks in is super important. I was asking AI to help with the syntax for these commands, and it initially had me falling into a pretty common trap. Luckily, I had a decent understanding of GlusterFS prior to this, so I called Mr. Copilot out on it. So the order that you list your blocks in your volume create command is the order that your files are going to be replicated in. For example, in their initial command, they had our 3 replicas going to 3 blocks on the same node, meaning that if that node goes down, you lose all 3 of your replicas, which is all of your data. The way you want to do this is to ensure that your replicas are spread out across multiple nodes, so list them in a round-robin fashion. All right, so we have our volumes created, and after starting them, I updated some volume parameters like the cache size, timeouts, thread counts, and I don't want to get too into it because I already feel like this is way too in the weeds. The next step is to mount our volumes locally on each Pi, which does seem weird, like the file systems on each drive are already mounted and the volumes are local, so why do we need to mount the volumes? But this is just so that we can write to the volume itself, not just the block within the volume. And you don't have to do this if you're never going to access your volume locally, but if you're using NFS or SMB, as we'll talk about in a second, you'll want to do this. But next, we are going to have to connect to these volumes from another system to see how they perform. The best and easiest way to do this is using the GlusterFS client, which is only really available on Linux. I think it was on Mac OS at one time, but this has been deprecated. Now, it doesn't mean you can't connect to it from a Mac OS or Windows machine, but you'll just have to set up NFS or an SMB share on your nodes, which, it's not that bad. I used one of my test boxes running Ubuntu, and after setting up GlusterFS client, it was pretty simple. It's just a single line for each volume in the fstab to get the volumes mounted, and the cool thing here is that you can specify multiple backup nodes in the event that the main one is down. Yay, high availability! At this point, we are done. We have our Gluster cluster running on our Raspberry Pis with 3 different volumes and the ability to connect to them across the network. I created an FIO script to test the performance under some different workloads, and well, it's not impressive, but calm down for a second. There is a reason for this. Looking at the numbers here, they're around 30 to 50 megabytes per second in the best case use scenario, which is like half the speed of a single hard drive. Not great, I know, but here's the thing. We very much bottlenecked ourselves here in a few ways. One is that we are running this on Raspberry Pi 5s. And yes, they are capable machines for a small SBC, but for a storage cluster that requires a decent amount of compute, the Raspberry Pis with their single lane of PCIe Gen 2 just aren't going to cut it. The other is the network. Anytime you replicate or distribute data across blocks, that has to go over the network between nodes, and we just have a 1 gig connection, meaning that the max we could ever get is around 120 megabytes per second. Even if we did have a 10 gig connection from our client to our switch, it doesn't matter since the Pis are talking to each other at 1 gig. The combination of these things is why I'm not really surprised at the performance. And depending on how this video performs and how interested y'all are in this project, I may do a version 2 of this setup where I fix a few things. One is I think we are going to try to get some NVMe drives in here somehow. 2 is we are going to need more PCIe bandwidth, which means I'll have to upgrade from the Pis. 3 is the network. We got to go at least 10 gig between the nodes, maybe even 25 gig. Who knows? And 4 is possibly a better power distribution system. Like, yeah, the adapters work, but there's definitely room for improvement here. Then, of course, whatever ideas you guys have down in the comments. But yeah, there it is. Overall thoughts? It's cool, man. It's a cool little setup. Is it perfect? No. Would I advise you to build this? I mean, you want to learn about GlusterFS? Sure, but to actually use it as a storage solution? Absolutely not. While GlusterFS is a highly available storage solution, this setup isn't really highly available. In a real highly available setup, you'd have each node in a different rack and possibly in a different location, and your networking would also have a highly available nature as well. And you can see here, all of our Pis are in the same rack on the same circuit, and they're all connected to the same network switch. So yeah, single points of failure everywhere. But this is home labbing, this is for learning, it's for fun, so whatever, mission accomplished. Anyway, that's it. If you liked it, then drop a like and subscribe if you want to see more stuff like this. I want to give a huge shout out to my YouTube members and my Patreons. You guys are my highly available storage cluster with fast drives, fast networking, fast cooling, fast everything. Y'all are fast. And if you're still watching, you're Seth. Thank you so much, and I'll see you in the next one.